So good morning. I am Krishna Kumar from Krishna's Classroom. We begin with another episode of analysis on Aaron. In fact, we are at a turning point. Because our final objective is to talk about functions defined from Rn to Rn, and then possibly talk about the derivatives and derivatives of different orders and so on. So we do want to do analysis on Rn or we want to discuss analysis of vector valued functions defined on Rn. This is our objective. So we have prepared the graph. We looked at the structure of Rn, and then we also introduce a metric, a natural metric on that space, and that endows us with the topology. And we are now in a position to talk about what is called continuity, and then possibly go beyond that and then talk about derivatives and so on. So let us start from R, a very familiar ground. I mean, this is how things work in mathematics. You start from a very familiar ground where you are fairly comfortable with all the notions that are already available there, and try to see how these ideas can be pushed across to new circumstances. That's our strategy. So we begin with R, which is the same as R1. So we want to talk about functions from f from some interval AB contained in R1 to, that is, real valued functions defined on some open interval in R1. Now note that we have all the necessary machinery to talk about open intervals and then the maths, and then now ask questions like continuity, differentiability, and so on. So we already know what exactly is a continuous function. Okay. Now want to see whether it is differentiable at a point x on this. When do you say f is differentiable at a point x on the interval a? So this happens if limit h tending to 0 of f of then, because here the assumption is that x plus h belong to the interval. This is the assumption that you have. So that f is defined on that, and therefore this difference makes sense because they are real numbers, so the difference makes sense. Now it can be divided by h because h is a number not equal to 0. Okay. So we let h tend to infinity. Sorry, h tend to 0. Take h so that this division is very well defined. Now you ask the question whether the limit exists or not. If the limit exists, then we write or we say that f is differentiable at x belonging to AB, and the derivative is of f at x denoted by is given is defined by limit f derivative of x as h tends to 0. Now this we are familiar with. Okay? That's the concept of derivative. There, of course, the structure of R has been heavily used, because you can subtract real numbers, or strictly speaking, add real numbers, multiply by scalars, and then divide by, if h is not equal to 0, then h inverse x. That means 1 by h is a real number, and therefore you can multiply this number by 1 by h. And then, of course, you can ask the question, what happens to this as h tends to 0? Because we are taking h not equal to 0. If the limit exists, then you say that the function f is differentiable at the point x, and it is denoted by this. Now, this whole thing has to be looked at again. So we try to rework on this, avoid the sensitive thing of dividing by h, and write it in a new form. Now you see that this means the following, that is limit or f of x plus h minus f of x plus h times equal to h times f derivative of x plus an error term which is a function of h, and x, of course, defined at the point x, which we shall not mention there. It is some function of h with the property that is of small order that is R of h zero. So this, okay. So you see that the crucial part is this. Okay, the difference. So you have this one f of minus is of the small order of h. That is the error term that you have. Small order. Now, one of the comfortable things that you have here, there is no division by h here. Okay, what exactly is this? This is the one that we have to look at. And this is where the derivative comes. Now we have to say what exactly the derivative means. Now you see that if you fix x, if x is a identified point and focus on that point on the interval AB, then you see that this is a number that you get. So therefore, this is actually multiplying h by a scalar, a real number. Okay. So we try to imagine more on that. Now you see that this defines what you call a linear transmission on R. What kind of linear transmission? So we have now from R to R. What is the nature of a linear transmission? T R to R, or T belongs to R. This means from linear algebra we know that there exists a scalar, say alpha, such that T h equal to alpha h. The converse is also true. Which means given a number alpha belonging to R, if you define Th equal to alpha h for every h belonging to R, then T is a linear transmission on R. Okay? So the identification of the real number with the linear transmission. And here what we say is that we look at this one as, so the alpha is in this case f derivative of x. Okay, the scalar so let me just call that. So we define A h. Now I am fixing x, keeping x fixed. Then of course this is true. So what happens is that here you can say that this is a, strictly speaking, a x, because I am keeping x fixed. Okay, and you see that ax is the ax belongs to L LR by the scalar f derivative of x, that is the derivative of f evaluated at if the limit exists, of course. So what have you done? You have taken fx plus h minus fx, from which a linear part has been removed. Okay? The linear part corresponding to that is f dash x into h has been taken out. And what is left is a error term RH, which is of higher order than mod h. Okay? So that as h tends to 0, RH divided by h goes to 0. So that in the limit of fx plus h minus f of x divided by h, limit of that is given by f derivative of x. Now this is what we have in our classical calculus, the concept of derivative. So now we are going to see derivative in a new form. So the derivative determines a linear transformation or not. Okay? So given the function, the derivative determines a linear transformation on R. Let us have a feeling for what kind of transformation it is. Okay. Let us do work little bit together. You can interpret x, f of x for x belonging to AB this interval is B. Now it's not necessarily the function need to be non-negative or anything, but just for convenience I'm going. Now take a point x on this. Now you see that f derivative at x is the slope of this line. Okay? So this is a line. What does this line look like? This line is, if you take h as a variable and x as fixed, then you see that this passes through the point x, and the slope of this is given by f derivative of x. Slope whenever it increases. Okay. So what does this give? What is the equation of this line? The equation of this line is, suppose you take a point xy on this, or hy on this. This is what you have. So you have f of x plus h equal to f of plus now this gives the equation of this one, where h is the new variable. So this is the point x, this is x plus h. What we are saying is that on this line, this point is f of x plus h, f of, this is this point. Okay, or you call that a generic point at x plus h, you have f of x plus h. What you are saying is that f of x plus h minus fx, that means this height, this is what you call f of x. So what you are saying is the following. See that f of x plus h minus f of x is m times, m is the slope of this line, times h. Okay, that m is given by f derivative of x. Okay, so this is what you have, f of x plus h minus f of this is true for any h. Okay, in R. So you see that the equation of this line is what? The equation of this line is y equal to f derivative of x times, what is the new variable that you have? H. Okay, right? And it passes through the point h equal to 0. Okay. So this is the equation of the line. Y equal to f of x plus into what? So in short way, what we are doing is you are shifting the origin. If you shift the origin here, then the equation of this line, the new variable, you can write down, and then you can get that this essentially gives the equation of the. Okay, so that's a simple thing to work. Maybe if you are getting confused with this variable x coming all along, now take x equal to x. Then what do you have? You have f of times h. What is h? Suppose I call this point x. So you suppose I designate this by then what do you get? F of x equal to f of x naught plus f derivative of x naught into x minus x. This is the equation. Now you see that this is the line. Suppose you write y equal to f derivative of x naught times x minus x naught plus f x naught. Then this is the equation of the line in the conventional language. Passing through x naught f of x naught with its rate. Okay, so I think to get for clarity and not to get confused with the variable x, I think it's better to use x equal to x naught without this, and that x naught you calculate everything. Then this is the equation of the line that you are getting. Y equal to mx plus. So the form y equal to mx minus x naught. See, the other expression that I wrote with h is that you are just actually shifting the origin to this point and then considering h as a new variable. Okay, right? So you write x minus x naught equal to h. Okay, so that's the change that you bring in. Or you shift the origin from 0, 0 to the point x naught fx naught, and then rewrite the whole thing. Then you will see that you get a new origin. You have the curve passing through that, and then you are talking about the derivative at this point, which is a line through the origin, and this line through the origin is of the form y equal to mx plus. I mean, that's just a small exercise that you can do. So the point is this: from you have from y minus fx naught, you have extracted out a linear part, and then what remains, that is the remainder, is a term of higher order in h, namely RH divided by mod h. As h tends to 0, it's equal to 0. So that is the remainder. Okay, right. Now our problem is this: how to push this idea across to higher dimensions. Now what we are eventually interested in is defined from some omega contained in Rn to R. That is vector value functions defined on suppose x naught is a point in omega. What will you How do you attribute a meaning to this? Now let us consider in mathematics you have understood something. Now you can tread along the same path to extend it to higher, different situations or similar situations. Look at complex valued functions of series. Okay. What happens? How do we define the derivative? Let Z0 be a point in C belonging to omega contains omega is an open subset of C. Now we want to define the derivative of f at Z0. How will you do it? You will just mimic what we have done so far. Can you do this? So what we want is we look at Z0 plus H minus f of Z0. This does not make any problem at all because it's a complex number. This is also a complex number. H is some complex number. Divided by H. So this is also sensible. Why? Because you can divide a complex number by a complex number to get a complex number. So what you end up with is a well-defined complex number for H not equal to 0. The situation is this. So this is in C. C, you are taking an omega point Z0. Then you have got Z0 plus H. This is the point. And now what you are doing is you are taking f, evaluating f at Z0 plus H, which is a complex number. Subtract from it f of Z0 and divide by H. H is a complex number. So this makes sense. Now the question that you are asking is whether limit H tending to 0. This is the question that you are asking. If it does exist, we call this the derivative of Z0, where H is of course going to H belongs to C. H is not equal to 0. Therefore, this is what you have. Okay? Right.
So, word by word, the kind of thing that we were discussing for a conventional derivative works for C. Okay? So that's very encouraging because C is very much like R2 with a certain additional properties like you have the vector space structure for it plus the multiplicative structure, and with the property that all the non-zero complex numbers have a multiplicative inverse. Okay, so when H is a complex number which is not equal to 0, then 1 by H makes sense as a complex number. Therefore, this idea just go across. Now you see that the helping factor in the first case as well as in this complex case are the following. In both the cases, in the first case R is a field. In the second case, C is a field, and therefore you can push this across. Okay, so that's the advantage, and because it's a field, 1 by h makes sense, otherwise it doesn't make sense. Now the problem that we are left with is this: you want to define derivative. I want to make some more remarks on this, but I will do that a bit later. Okay. Want to talk about functions defined from. Let us start with, in a modest way, Rn to R. You can work here because you know there is difficulty. See, if you work from R to Rn, that means vector valued function of a real variable. Okay. If you work with a vector valued function of a real variable, then can you push this across? So this is the whole point. Our conventional derivative doesn't make sense. Suppose f is defined from R to R or some interval AB where AB is contained in R. That means f is a vector value function. On AB, you have the topology of R. On Rn also has it's a metric space as we have described earlier. So both these are metric spaces. Therefore, you can talk about continuity of f and possibly even differentiability of f, because we have the necessary machinery on the spaces to support whatever we are doing. But let us now start working out the derivative. So formally, our derivative, f derivative at x naught will be, if it makes sense, limit h tending to 0 of f of x naught plus h minus f of divided by h. This is our standard if the limit exists. Okay. And all the other conditions are that for x naught plus h is such that x naught plus h and x naught belongs to the interval a, b, etc. These are the routine conditions that you have. And then you can talk about h going to 0. There is absolutely no difficulty, because if you look at the numerator, what you get is a difference of two vectors. And this is well defined because you have got the linear space structure on the range space R. So you can talk about the difference of, because you know that this is a vector in Rn, this is a vector in Rn, therefore the difference is well defined. What about h? H is a real number. Because it's a vector space and h is not equal to 0, you can divide by this. When you divide by this, then you get another vector in Rn. So this is well defined. So this part is well defined. Now the problem that you ask is this: whether the limit exists or not. So if you write this in the component form, suppose f is written as then you see that f of x equal to f1x So combined interval. Okay. So it's a map from the interval AB to R at some point. So this is X. What about this? You are taking X plus H to X minus H. So you are taking a neighborhood of this, and this is X minus H. Or let me put X naught here, so that you don't confuse with this. Therefore, this is Fx naught. So what you have? You have f of x naught plus h is this f of and what about this difference? This difference is then what you have in the numerator. Therefore, f derivative at x naught is equal to limit h tending to 0 of the following: 1 by h This is just the vector addition. That's not that. And you can, h is a real number which is not equal to 0, therefore 1 by h is defined as a real number, therefore you can multiply that. So everything is well defined, and you can ask the question whether the limit exists or not. So that amounts to getting this, see, limit of h tending to 0 of fn x naught plus h minus fn divided by. So that would give you, if the limits of all these terms do exist, then you are going to have the following. Equal to f1 derivative at x naught okay. So this you define as f derivative of x naught. So each component is a real valued function. You already know what you mean by the derivative of that, and that is well defined. So you get this. So this is the formula that works for functions defined from interval AB to You can, there is absolutely no complication at all. Everything makes a smooth sail. And we already seen that for the complex case also, everything goes through very smoothly. Okay? But let us see, suppose I change the domain to R, where n is greater than 1. Let's start from simple situation. Function defined on Rn, an open subset of Rn for n greater than 1. Then what happens? We try to mimic. Yes, that's how we normally go about it. And the moment you get stuck, you try to overcome that. Okay? So what have we done so far? We have had a look at the derivative in R1. Just try to reinterpret it in some convenient way. Then we looked at the f defined from R to Rn. That means vector valued functions. There again you can use the previous knowledge to define what's the derivative. So it is sensible to define derivative as component wise derivative. Everything absolutely smoothly goes through, provided the derivatives do exist. Okay. Now let us consider this situation. I am taking the case for n is greater than 1 and an omega in R. So what do I have? I have now a function fx. So I take x as the variable. Then omega and x naught. Let x naught belong to this your omega. So let us try to work out the same idea. Okay? What do? We take a increment. Now in this case the increment is going to be a vector. Okay? So we take h r. Okay? Then x naught plus h such that so that you are comfortable, f is defined, and then you have take this one f of x naught plus h minus f of x naught. There is no problem. This is a real number, this is a real number, and the difference is different. So even if it's a vector valued function, this difference is well defined. Okay? What you would do normally, try to get this. Okay? Does this make sense? It doesn't make any sense because you are dividing by a vector in R and division is not defined in R. Okay? You have only a linear space structure. You are divided by a scalar which is non-zero. but not by a vector. Okay, therefore this does not make sense. In fact, you might say, okay, in C we could get away with it. What did we do? In C you had fz plus h minus fz divided by h, and the h was a complex number, a non-zero complex number. But then in C, it worked. But why? Because in C we have division by non-zero complex numbers possible. And why? Because of the fact that as C is a, you see the field structure is what helped you. It's the field structure of C that helped you. It's the field structure of R that we are able to divide. Okay, and make sense. But in Rn, for n greater than 1, you might say that except in C, which is in a way R2 with a well-defined multiplication. Which makes or endorse R2 with a field structure. So in that case we could get through without difficulty. But in general such a structure is not possible. For instance, you take R3, you cannot give a sort of endorse this with a field structure which goes gels smoothly with the linear space structure. So there is a problem. Okay. Therefore, our conventional idea will not work. Why? Because 1 by h is no more a vector. So for h, that is the problem. Okay? Had this been possible, I think we could have pushed across our old idea. But this is no more gravity. Therefore, our conventional way of defining a derivative is no more going to be. Now, it is in this context that we actually try to rework the whole thing. Okay? What did we do? We try to avoid this division. Okay? So we had this problem, in R1 we had this problem, or in C we had this problem, so we were trying to work on that. Okay? In both R C did not encounter any problem to divide. Still, we circumvent this problem. So our task is now rework the concept of derivative by avoiding division by h. So we went to the drawing board. And found that went back to the drawing board to rework the concept of derivative in the case of interval a b to avoiding division by this is important. Try to avoid this. We actually circumvent this one, and we found that this is essentially limit h tending to 0 f of x naught plus h minus f of x naught divided by h equal to f derivative at x naught h naught equal to 0, and then we know that h goes to 0. This is the limit that we have. limit exists is what f of x naught plus h minus f of x naught equal to f derivative at x naught times h plus the error term r of h, where the error term RH is such that zero. This is equivalent. Fortunately, in this formulation, we don't have the difficult step, namely dividing by h. And here in this statement, we have written RH divided by mod h. Okay, and there's a possibility that this can be reformulated for vectors in R, because the only thing is that wherever this modulus comes, you will have to replace by norm. Okay, and you also in this context observe that mod h equal to 0 if and only if h equal to 0. So if the norm of a vector is equal to 0, then that is if and only if the vector itself is 0. So we can essentially work with that. Whereas this won't work. You see, you cannot write f of x naught plus h minus f of x naught divided by mod h. Mod h you can write, but it doesn't give you the derivative anyway. Okay? Because you see that when you write mod h or norm h, what happens is that you are allowing h to go to, or length of h to go to 0. Okay, right? Whereas the increment that you take in is all around. Okay, so I want to make also one more comment about the complex case. You would have noted that in the complex case, the condition that h goes to 0 is much more stronger than the condition that h goes to 0 in R. What happens? In R, you see that this is the point x naught, then x naught plus h is either here or x naught. See, when h goes to 0, you are moving towards x naught either in this direction or in this direction. So this is the real case. So whenever you write limit h tending to 0, it means you are allowing h to go to 0 from the right or from the left. There are only two directions. And the demand is that the limit exists for these two limits and they are the same. Okay? Whereas when you go to the complex case, you have the complex plane, you have the point z0. When you are talking about z0 plus h, you are taking a neighborhood of z0. And then allowing h to go to 0. In fact, h can go to 0 in very many ways. A neighboring point is any point in this, and that point can go to 0 in so many different ways. Okay? That's the problem. So it can go to 0, h can go to 0 from all around. It can even go, take a weird path and go to 0. Now when you say the limit exists, what you are saying is that irrespective of the path along which h goes to 0, or x naught plus h goes to x naught, the limit should exist or it should give the same number. So there are infinitely many ways in which this can happen. In all cases, the limit should exist and should be equal. It's an awful demand. You know, a lot of conditions are there on that. It's not like the two directions, h going to 0 from the two directions. It's actually from all sorts of directions. So that's the problem. And so you see that the condition that you have in the complex case is very stringent the moment you say that h goes to 0, although it may look very innocent. Okay, h can go to 0 or z0 plus h can go to z0 in very many ways along all sorts of paths which take you to the point z0. So in all those cases you require the limit to exist and should be the same. That means whenever the limit exists, it has happened under a very, very strong condition. That is why you have a very powerful result which says that if f is differentiable at z0, then derivatives of all orders exist. Okay, and even the power series that you can develop in the neighborhood of that would converge to the function. Okay, so you can develop this into a convergent power series. Now that's a very powerful result that you obtain from that. It is mainly because of the strong conditions that you impose on the limiting condition. It is less stringent in the real case, but in the case of Rn, now you see that you cannot do much. Okay, if you work with the conventional concept of derivative, it doesn't work because that ratio doesn't make any sense. This is the problem. Okay, so this ratio does not make any sense when h is a vector. Okay, therefore we rework the whole thing and we rework it in this form. And this is the way in which mathematics goes forward. Okay, and maybe I am just talking to the students who are one day or other, someday or other, going to be researchers in mathematics. And for them, you see that you have to keep your eyes and ears completely open, so that how do you meaningfully generalize a concept? And wherever you stumble, you will have to work out some new ideas or repack the old into a new bottle. Now this will have to be done, and this is what we did. As we encountered no problem when we talked about functions of a real variable to define the derivative, we could very smoothly go into the complex valued functions of a complex variable or even vector valued functions of a complex variable. Ideas to go. What mattered was what you can do under domain. Then we found that if you were to talk about functions defined on, say, Rn, okay, where n is greater than 1, then you are in trouble because this ratio does not make any sense. Okay. Therefore, it is not that you give up at that stage, but we try to rework the whole thing. That's why we went back in the beginning itself. We had a look at what the derivative is and what does it give and so on. And we just indicated at that stage that this number, or in this case, this is something that you get, can be reinterpreted as defining a linear transformation. Okay? This can be reinterpreted as defining a linear transformation. Once again, you see that the problem is here also, because this is a vector. Okay? This is a vector. Okay? Right? So if this is a number, then you are through. F dash x naught times h is a number, so this becomes a vector. And there is no imbalance coming from that. But then you cannot expect that. So what else you can do? This should be defining a map on Rn, so that eventually what you get here should be a vector. Okay? And its dependence on h is linear. Therefore, you get f dash x naught defining what you call a linear transformation. Okay? So, what vector should be there? F is, suppose f is a map from Rn to Rn. Then this is a vector in Rn. This is also a vector in Rn, the range space. Now you see that h is a vector in Rn. If this is a scalar, what you get? You get a, suppose n is different from m, then this is going to be a vector in Rn. So you are talking about a vector in Rn equated against a vector in Rn. Therefore, this cannot be a scalar. Okay, in general. Okay. So what do you need? You see that this has to be conceived as a map which acts on Rn to give you a vector in Rn. So that this is for consistency, this is a vector in Rn, this is a vector in Rn, they can be equated, and this is a vector in Rn. Oh, that's no problem, because this is the leftover. The leftover is a vector in Rn. Okay? So, right? So, these are the some of the things that you have to work on. So, we will have to reinterpret the derivative to generalize it into the larger scenario. That's exactly what we are going to do. Okay? So I think I stop here this first initiation lecture on this topic of getting the derivative. And now we have to completely rework the concept of derivative, as we have suggested what to do. And now, once that is done, then you see that your ideas can be pushed across. Now this leads to the wonderful concept of what is called Freshian derivatives. Okay? So I stop here, so next time I will start from here and then carry you through the more general situation. So thank you very much.